All right, diving into some really cool AI research today. Buckle up. We're taking a close look at this paper called AlphaDrive, Unleashing the Power of VLMs in Autonomous Driving via Reinforcement Learning and Reasoning. So for anyone who wants that super quick TLDR, basically they've come up with this new framework called AlphaDrive, and it uses vision language models, VLMs, for planning how a self-driving car should navigate. The big thing here is how they combine reinforcement learning, specifically something called Group Relative Policy Optimization, or GRPO-based reinforcement learning, with this two-stage training process for reasoning, first supervised fine-tuning, and then they bring in the RL. And guess what? It really seems to work. They're seeing way better accuracy in planning, especially in those tricky edge cases, those situations that don't happen very often. Oh, and it's more efficient for training too, which is always a good thing. Plus, get this, the model is showing signs of being able to come up with multiple solutions for complex scenarios.
Yeah, that's one of the things that really jumped out at me too.
So let's break down this AlphaDrive paper even further, shall we? One of the first things that caught my eye was how they're trying to address some of the, I guess you could say, limitations of those end-to-end autonomous driving models. I mean, we've seen huge progress with these models. Don't get me wrong, they're getting really good. But they kind of struggle when they encounter something unusual or out of the ordinary, something they haven't seen a lot of examples of during training. Like they don't always have that common sense you'd expect from a human driver.
Exactly. And the paper gives this perfect example, right? Imagine a vehicle with traffic cones on top. Now, a typical end-to-end model might just see those cones and go, oh, road closed, slam on the brakes. Makes sense in a way, but potentially unnecessary, right?
Like a human would probably be able to figure out, oh, those are probably just being transported. But these models, they're amazing at pattern recognition, but they don't always have that deeper level of reasoning that we humans kind of take for granted.
Yeah.
And that's where these vision language models, VLMs, come in. I mean, we've already seen how much of a game changer large language models like GPT and DeepSeek have been in areas that really require complex reasoning, you know, things like coding and problem solving.
Absolutely.
So now VLMs are bringing that same kind of reasoning power to the world of visual information. It's like they can see and think at the same time. And you've got these really impressive models like OpenAI's O1 and DeepSeek's R1. I mean, they've really shown what's possible when you combine reasoning with reinforcement learning. So the folks behind AlphaDrive, they saw that same potential in the realm of self-driving cars. It's pretty exciting.
For sure. And what's especially interesting here is how they're tackling this challenge of bridging the gap between how a VLM perceives the world and the very precise control you need for driving.
Right. Because it's not as simple as just seeing the road.
Exactly. So a lot of the current attempts to use VLMs in this field, they sort of fall into two main categories. Some of them focus on using VLMs to boost what we call scene understanding, you know, getting better at recognizing objects, predicting what other cars or pedestrians might do, that kind of thing.
Makes sense, like making sure the AI gets what's going on around it.
Right. But then there are others who are trying to use VLMs directly to plan the car's trajectory. So like, where should the car go? How fast should it go? When should it turn? All of that.
Okay. So let's dive into that second approach for a minute. The paper talks about a fundamental challenge with just directly asking a VLM to output a driving trajectory. And it comes down to the fact that VLMs, they essentially operate in this world of language. They're really good at understanding and generating text. That's their bread and butter.
Yeah, that's their forte.
But plotting out the exact path of a vehicle, you need insane numerical accuracy, you know, down to centimeters and milliseconds. That's not really their language, so to speak.
No, not really. It's like asking a poet to write a physics equation.
Kinda. So then there's this alternative, right? Which is to use VLMs for that high-level language-based planning. So instead of saying, move the steering wheel exactly 12.5 degrees to the left, you might say, change lanes to the left in 100 meters, something like that. And that avoids that whole problem of direct numerical prediction. But up until now, that approach has mostly relied on standard supervised fine-tuning.
Right. And what the authors of this paper are arguing is that maybe that's not the best way to do it, that we might be missing out on some potential performance gains by not taking advantage of more advanced training methods, not to mention the potential cost implications.
Yeah, because training these models can get really expensive. So essentially the big question they're asking is, how can we take all that power of reinforcement learning and reasoning, which has been so successful in making these general large models better, and how can we apply it specifically to the world of autonomous driving planning using VLMs?
Right. How can we get these VLMs to not just drive well, but also learn to drive well more efficiently.
Exactly. And that's where AlphaDrive comes in. It's their answer to this challenge. They've basically built this framework that's designed for autonomous driving, but it takes advantage of both the strengths of VLMs and this group relative policy optimization-based reinforcement learning, GRPO. And they've got this two-stage training strategy that really seems to boost the model's reasoning about driving situations.
Yeah, and they're claiming some pretty significant improvements in planning performance.
Yeah, for sure. Plus, they're seeing better training efficiency and even these really cool emergent capabilities where the model can actually consider multiple valid actions.
Yeah, that's really interesting. Like, it's starting to show signs of being able to think outside the box a little bit.
Totally. Now, here's where it gets really interesting, especially of the more technically minded folks listening. The researchers, they identified a few key roadblocks in just trying to apply those existing RL and reasoning techniques directly to autonomous driving planning. Like, it's not as simple as just plugging them in.
Yeah, you've got to make some adjustments.
Exactly. So the first big challenge is reward design. In a lot of typical RL tasks, the reward signal is pretty straightforward. Did you achieve the goal or not? Yes or no. But driving, it's way more nuanced than that. Like a slight steering correction is not the same as slamming on the brakes in an emergency.
Right. Very different levels of importance.
But a basic reward function, it might treat those two things the same way.
Exactly. And that's not ideal for training a model to drive safely and effectively.
Nope. Then you've got this whole issue of multiple valid solutions. Like, think about driving on a wide open highway. You could maintain your current speed, you could speed up a little, you could slow down a little, and any of those might be perfectly fine.
Totally. Like, there's no one right answer in a lot of driving situations.
Exactly. So if your training data only shows one correct action, and you penalize the model for doing something different, even if it's perfectly valid, well, that could actually mess up the learning process.
It could make the model less flexible, less able to adapt to different situations.
Exactly. And then the third big challenge they highlight is the lack of good quality reasoning data sets, specifically for autonomous driving. Like in other fields, you have tons of examples showing how to solve a problem step by step. Like in math, you have all those worked out solutions.
Right, showing the logic behind each step.
Yeah. But for driving, capturing that kind of detailed reasoning, like why a driver made a specific decision in a particular situation, it's super complex and expensive to get that labeled data at scale.
It's not easy, and that lack of data can really hinder the development of robust AI drivers.
Okay, so those are the challenges. Now, how does AlphaDrive actually address these issues? Well, a key part of their framework is this use of group relative policy optimization, GRPO, for the reinforcement learning.
And I think that's a really smart choice, given the challenges we just discussed.
Right. And they specifically chose GRPO over more common RL algorithms like PPO or DPO because it's shown better stability and efficiency during training. We've seen that in other models like DeepSeek R1.
Yeah, it seems to be better at handling these more complex scenarios where there might be multiple good solutions.
For sure. And that group relative part of GRPO, that seems particularly relevant here, right? Because instead of just looking at each action in isolation, it considers a whole group of potential actions and learns which ones are better within that group. So in a driving scenario where you have a few good options, this seems like a much smarter way to train the model.
It's learning to compare and contrast different options rather than just trying to find the single best one.
Exactly. And the authors suggest that this might actually be one of the reasons they're seeing those emergent multimodal planning capabilities.
That makes sense.
Now, on top of using GRPO, they also incorporate these 4 specific GRPO reward functions that are really tailored for driving. So the first one is what you might call a standard planning accuracy reward. It basically measures how well the model's planned actions match up with the actual ground truth driving actions from the data. And they specifically use the F1 score for this.
Ah, interesting. So why the F1 score in particular? What's the advantage there?
Good question. So the F1 score, it balances precision and recall. And early on in training, the model might be kind of all over the place. It might spit out actions that make no sense, or it might try to cheat the system somehow. Using the F1 score helps to avoid those issues. It makes sure the model isn't just making a ton of predictions, most of which are wrong. It would be high recall.
Right. It's not just about quantity, it's about quality too.
Right. And it also prevents the model from being too cautious and only making a few predictions. Even if those are correct, that would be high precision. It encourages the model to find a good balance between the two.
That makes a lot of sense. So it's like finding the sweet spot between being bold and being accurate.
Exactly. So on to reward number 2. This one is called the action-weighted reward. And this addresses the fact that not all driving actions are equally important. Some actions, like braking and steering, those are super critical for safety, right? So those actions get higher weights in the reward calculation.
Okay, so it's like saying, hey, model, pay extra attention to these actions because if you mess these up, it could be really bad.
Yeah, pretty much.
Yeah.
The model gets penalized more heavily for making mistakes in those safety critical areas. And that encourages it to learn those things really well right from the start. The key idea here is that not all driving errors are created equal. And AlphaDrive reflects that in how it learns. It prioritizes those safety critical actions above all else.
Really smart. Really smart. So what about the third reward? What's that all about?
So the third reward is all about planning diversity. Because, like we were talking about before, there are often multiple valid ways to handle a driving situation. So this reward, it encourages the model to explore and come up with a variety of different plans that could work.
So it's not just finding one solution and sticking with it. It's about being adaptable.
Right. And this prevents the model from just converging on one single output, which might not always be the best choice.
Makes sense. You don't want the model to get stuck in a rut.
Nope. And then the final reward is the planning format reward. And this one basically encourages the model to structure its reasoning and its final plan in a specific way using these special tags like think and answer.
Okay, so it's like giving the model a template to follow.
Yeah, kinda. And this structured output, it not only makes it easier for the researchers to analyze what the model's thinking, but also it seems to help with training stability. Kind of similar to what they saw with models like DeepSeek R1, which also use structured outputs.
Right, it gives the model some guidelines to follow.
Okay, so that's the reinforcement learning side of things. Now, let's talk about that two-stage reasoning training strategy. The first stage is called Supervised Fine-tuning, or SFT. And basically, they're using a really powerful large language model, something like GPT-4, to create this data set of detailed reasoning processes for all sorts of driving scenarios.
So they're using one AI to teach another AI how to think about driving.
Yeah, exactly. And then they use this knowledge to give their VLM a head start through SFT. It's like, first, the model learns how to reason about driving from this top student, GPT-4o, and then it practices and refines those skills through real-world driving scenarios using reinforcement learning.
That's actually a really clever approach, especially given how hard it is to get those human-annotated reasoning data sets for driving. This knowledge distillation technique, it's a really smart way to bootstrap the model's reasoning abilities.
Totally. And then that second stage is where the reinforcement learning we were just talking about comes in to really fine-tune the model's planning skills. And that SFT pre-training, it's super important because it helps to avoid problems like hallucinations, where the model might generate stuff that sounds plausible but is actually wrong.
Right, it's like making sure the model has a solid foundation in reality before it starts exploring on its own.
Exactly. And it also helps to prevent instability during those early phases of RL training. So it's kind of like setting the stage for success.
Okay, so that's the training process. How about the experiments? How did they actually test this thing out?
Good question. So they used this large-scale, real-world driving data set called Meta-E, and they trained their AlphaDrive model, which is based on this architecture called Qwen2VL2B. And they used a pretty significant amount of computing power for all of this.
Of course. Training these big models, it takes a lot of juice.
Definitely. And they looked at two main things in their evaluation: how accurate the model was in making those high-level planning decisions, and how good the reasoning processes were that the model generated. So for the planning accuracy, they used that F1 score again to measure how well the model did with things like steering and speed control.
Makes sense. And for the reasoning quality, they used those standard text similarity metrics like BLU4, CIDR, and Meteor to compare the model's reasoning with the annotations they had.
Exactly. So what did they find? Well, the results are pretty impressive. AlphaDrive showed a huge improvement in overall planning accuracy compared to models that were just trained with supervised fine-tuning on that Meta-E dataset. They saw something like a 25.52% increase. And get this, when they trained it on only 20% of the full dataset, they saw an even bigger jump, like a 35.31% increase.
Wow, that's a massive difference, especially with less data. That really highlights how much more efficient this approach is.
Yeah, it's pretty amazing. And those improvements were especially strong in those critical actions like steering and accelerating and braking, which really shows how effective those GRPO rewards and the reasoning training were. They also found that AlphaDrive got the highest scores in reasoning quality compared to the other models they tested. So it's not just driving better, it's also thinking better, so to speak.
It's like it's understanding the why behind its actions better.
Exactly. And they also did these really thorough ablation studies, which I always appreciate. They wanted to see how much each part of their approach was contributing to the overall success. So they tested each of those 4 GRPO planning rewards individually, and it turned out that every single one of them helped to improve performance, with the best results coming when they used all 4 together.
So it's like each reward adds another layer of refinement to the learning process.
Yeah, exactly. They also did an ablation on that whole reasoning training strategy, and they found that incorporating any kind of planning reasoning helped to improve performance, especially for those more complex longitudinal control decisions, like when to speed up or slow down.
Makes sense. You need more than just basic reflexes for those kinds of decisions.
For sure. And this also confirmed that their 2-stage approach, that SFT warm-up followed by RL, that was the best way to get those really good reasoning capabilities.
So it's like a 1-2 punch.
Yeah, and their analysis of how the amount of training data affected performance, that really showed how efficient AlphaDrive is. Even with a lot less training data, their RL-based approach still beat out that model that was only trained with SFT. And that's a really big deal for real-world applications where getting tons and tons of driving data and labeling it perfectly, well, that can be a huge bottleneck.
It's a major practical consideration, so it's exciting to see that they're able to achieve such good results with less data.
Absolutely. Now, beyond all those numbers, they also gave some really interesting qualitative examples that showed how AlphaDrive could actually generate multiple reasonable driving plans in these tricky situations, whereas the SFT train model usually only came up with one output.
So it's like AlphaDrive is able to consider different options and weigh the pros and cons.
Yeah, that's a great way to put it. And that ability to think about multiple possibilities, it feels like a big step towards having more robust and flexible self-driving cars, cars that can adapt to all sorts of unexpected things.
Totally. And if you think about it, being able to generate multiple solutions in a tough spot could be a huge advantage for safety and efficiency. Like, a higher level control system could then look at those options and decide which one is the best in that moment.
It's like having a co-pilot that can give you suggestions.
Exactly.
Now, the authors are also very upfront about the limitations of this work. They point out that AlphaDrive, at least in its current form, it can't really handle those more complex driving maneuvers, things like lane changes. And that's mostly because the data set they used doesn't have a lot of annotations for those kinds of actions.
So it's kind of limited by the data it was trained on.
Right. And they also acknowledge that the reasoning data they created using those large language models, it's essentially pseudo-labeled, right? It wasn't directly created by humans. So it's possible that there are still some inaccuracies in there, or maybe it's missing some really important factors that a human would consider.
Yeah, so there's always room for improvement.
For sure. And they emphasize the need for more validation, more testing, to really refine that reasoning data and to see just how far they can push this AlphaDrive framework.
Makes sense. Always got to keep iterating and improving.
Absolutely. So this brings us to a really interesting question for you, our listener, especially those of you who are deep into the technical weeds of this stuff. Given how quickly we're seeing progress with AlphaDrive in combining reasoning and reinforcement learning for autonomous driving with VLMs, what are some of the cool new ways we could annotate data, or maybe even create completely new simulation environments to speed up the development of these truly robust and adaptable self-driving systems? Systems that can handle all the complexity and unpredictability of the real world. It's a pretty exciting challenge to think about.
It is. It's like, what are the next big breakthroughs waiting to be discovered in this field?
Exactly. And with that, we'll wrap up this deep dive. Thanks for joining us.
Yeah, thanks for having me. It's been a great discussion.
Always a pleasure. Until next time.
See you then.